Hello everyone, today we are going to talk about block 5, relation, equivalence relations, and equivalent classes. Last week during tutorial we actually talked quite a lot about this, so I hope everyone here have some idea of what relation, equivalence relation, and equivalent classes are. But here is the first definition. So let A and B be two sets. A relation R between A and B is a subset of A Cartesian product B. That is a set R, so that R is a subset of A Cartesian product B. Just by looking at the definition, we know that R is a collection of ordered pairs. What do I mean by that? For example, let's say we have A, B are in R. Okay, what does this mean? This whole thing means that our A is in A, B is in B, and A is related, or A has relation with B. You might still not really understand this, so I'll give you another example. Let's say this. Consider the order relation let's say smaller than or equal to. Okay, so this is our relation, and I will define it more properly. Okay, let's call this R. Okay, what I mean by that is R is a set of ordered pair AB such that A is smaller than or equal to 2. No, not 2B. Okay? And I'm telling you, this whole thing is a subset of, let's say, integer Cartesian product integer. Okay, so it's a subset of Z2. Now, let's have some example here. Let's say order pair 1, 2. Okay, this would be in R because 1 is less than or equal to 2. Alright, let's say something else like 2, 2 would also in R because 2 is less than or equal to 2. This thing might be confusing because some of you might say, oh, 2 equals to 2 is not less than or equal to. This is true because this symbol means less than or equal to. Okay, since it's equal, so it satisfies this condition as well. Let's think about some other things. Let's say 3. If we have 3, 1, well, this will not be in R because 3 is not less than or equal to 1. Okay, or so let's say 10, 9 would not be in R because 10 is not less than or equal to 9. Alright, I'll give you another example. Let's say another relation, let's call it R prime, ordered pair AB such that A equals to the absolute value of B. Alright, and this is a subset of 0 to infinity Cartesian product R. Alright, now based on this, you know that our A is in 0 to infinity and B is an element of real numbers. Oh, I need to mention this. Make sure you distinguish your notation for real number and R. Alright, this is real number and this means relation. They are different. Please don't mix them up, right? Anyway, in this case, okay, let me write more. This would be our A, this would be our B, alright? In this case, let's use the same thing from the previous example. Let's consider the order pair 1, 2. 1, 2 would not be in R prime because 1 does not equal to the absolute value of 2. Alright, however, 2, 2 would be in R prime because 2 equals to the absolute value of 2. What else? Let's say 10 minus 10 would be in R prime as well because 10 equals to the absolute value of minus 10. 3, 2 would not be in R prime. Well, because 3 does not equal to the absolute value of 2. Alright? Now, the next part, I wrote relations and functions here because relations are actually more general than functions. We can consider A as the domain of a function, B as a codomain of a function. Well, in this case, though, this will allow us to describe curves or regions. I'll give you an example as well. For example, let's say R equals to the order pair AB such that A squared plus B squared equals to 1. And this is a subset of R, Cartesian product R. Well, this relation actually describes something everyone's quite familiar with. Okay, this is R times R. This relation will be the unit circle. Okay, that's perfect. A unit circle. So this relation R is the unit circle in R2. What I mean by unit circle, I mean the radius. This is 1, 1, minus 1, and minus 1. Alright. Now your homework would be to check if R is an equivalence relation, which is something we'll talk about later, but I want you to go home and check, okay? The other thing is another question. Is R a function? Well, just by looking at this, we might say, oh, it looks like a function, right? Well, think about back in high school, how do you check if you have the curve of a function or just have a figure? How do you check if it is a function? How do we check? We have a test called vertical line test. Which means you draw a vertical line, okay? And if this line only passing through one point for all your domain, if this vertical line pass through only one point at any of your domain, then it is a function. If it passes through more than one point, then it's not a function. For this one, apparently it's not a function. Well, let's write it here. Fails vertical line test. In this case, you can see that our relation is actually more general than functions. Another example, let's see our R is ordered pair AB such that A equals to B squared. And this is also in R2. Alright, then the graph of this will be something like, okay, this is not horizontal enough. Something like this. Alright, again, let's do a vertical line test. Passing through more than one point, which means this is not a function. Now I wrote the formal definition or formal theory of vertical line test. Please have a look at this. I remember one of your learning objective for this section is check if a given relation is a function. So make sure you know how to check that. I'm not gonna read this for me, just go home and read it yourself, okay? Now let's talk about equivalence relation and the equivalence classes. Usually those two are together, so I don't want to separate them. Definition. Oh, here's a typo. This is equivalence. It's Q here. Oh my god, I don't know how to spell equivalence. Okay, let's cross it out. It's equivalence. I'll fix this later, so on your updated file it's gonna be correct. Anyway, an equivalence relation R on a set S is a relation such that it is reflexive, symmetric, and transitive. I hope I don't have to repeat what those means anymore because, well, we did a lot of this already in tutorial. I do hope you can go over your tutorial worksheet. I'll upload the tutorial worksheet for the last week as well, so that you can go over the activities we did in class, have fun with it. Anyway, the other definition, this is for equivalence class. I know some of you don't understand what equivalence class is. This is just the equivalent class of X is like a collection of Y such that x and y has this relation, have this equivalence relation. Alright, I'll give you some example later, but let's just move on for now. Here is a theorem that's really important. So it's saying that if you take any x in S belong to some equivalence class, then any two different equivalence classes are disjoint. Well, I remember in tutorial I asked you guys to prove it yourself. If you pick two equivalent classes on a set, then they are either disjoint or the same, right? So here they mention that two different equivalence classes, and that's why they have to be disjoint. The proof is in the book. I hope you can prove it yourself first and then check with course notes. This theorem is quite important when we talk about partition, so I do hope every one of you can prove this. Anyway, let's move on to questions. Consider the following relation on a set of integers x, y, such that x plus 2y is divisible by 3. And we want you to prove that R is an equivalence relation. Well, first of all, we need to show that it's reflexive. How do you show it's reflexive? Well, you need to show that for all elements in, it's on a set of integers. So you want to show that for all integers, let's pick an arbitrary element from integer z, let's say x. We want to show that x has relation with itself. How do we show that? Well, x plus 2x equals to 3x, which is divisible by 3. Therefore, this shows us that x and x have relation, which means this relation is reflexive, not symmetric. So we suppose x and y has relation. This gives us that x plus 2y is divisible by 3, which means we can write it as 3k for some k in z. Okay? Now we need to show that y has relation with x. So we need to consider y plus 3x. Well, from this, we know that, x equals to 3x minus 2y. So we can substitute that. Okay, let's write it here. Then y equals to 3 times 3k minus 2y, which will give us y plus 9k minus, did I write this wrong somewhere? Y plus 3x. So it's, oh yeah, that's why. It's y plus 2x. So it's y plus 6k minus 4y, which will give us 6k minus 3y, which is divisible by 3. This means that y has relation with x. So it's symmetric. The last one, I'll write it here. Transitive. So you want to suppose x and y has relation, y and z have relation, and this will give us x plus 2y equals to 3k. Okay, we used k already, so let's use something else. Equals to 3m. Y plus 2z equals to 3n. And we know that m and n are integers. Now you need to consider x plus 2z. Well, we see x here, we see 2z here, so you want to add them together. This will become 3m minus 2y, that's your x, plus 3m minus y, which becomes 3m plus 3n minus 3y, which is clearly divisible by 3. By 3. This tells us that x and z has relation. Therefore, it's transitive. Now we're done. Since it's reflexive, symmetric, and transitive, we know that R is an equivalence relation. Part 2. Describe the equivalence class of number 5. So we want to describe this. Well, this would be a collection of, let's say, x in integer such that x and 5 have a relation. So we can write as x and 5 has relation. What does this mean? This means x is in z. Well, we know that x and 5 have a relation if and only if x plus 2 times 5 is divisible by 3. So I write it as 3l, where l is integer. Well, this is x equals to 3l minus 10, where l is integer. Alright, and that's it. Next question, x and y have a relation if and only if x minus y is even. It is an equivalence relation. Justify your answer. Same thing. First, reflexive. You want to show x and x have relation. Since we know x minus x equals to 0, which is even, we know that x has relation with itself. So it's reflexive. Number 2, symmetric. Suppose x and y have relation. This gives us x minus y is even, so we can write it as 2k, and k is an integer. Now you want to consider y minus x. Well, y minus x is minus or negative of x minus y, which would be negative 2k. This is even. So this shows us y and x have relation, so it's symmetric. Number 3, transitive. You want to suppose x, y have relation, y, z have relation. This gives us x minus y is 2k, y minus z is 2l, k and l are integers. Now you want to consider x minus z. Well, we have x here, we have minus z here, so we can add them together. This will give us 2k plus y plus 2k minus y, which will give us 2k plus l, which is even. Therefore, x and z have relation, so it's transitive. Well, since since R is reflexive, symmetric, and transitive, we know that R is an equivalent relation. The last question I'll do is really similar to your homework question, so let's do it quick. I'm doing this question because I know some of you are confusing about this. So the first one, reflexive. What are you trying to show? Are you trying to show that A has a relation with A? Or some of you might think we want to show AA has a relation with AA. Okay? This is not true. This is not what you need to show. Okay? So this is what I usually tell my students. If you see this symbol, you know that this has a relation with this. So this will be your x. This will be your y. You want to show x has a relation with itself, which means you want to show AB has a relation with AB. Okay, I'll write it here. Want to show AB has a relation with AB. Okay, since we know that A plus 2B equals to A plus 2B, so it is reflexive, okay? Okay, let's write this. Number 2, symmetric. We suppose AB has relation with CD. By the way, if you, I saw some of you might not understand the notation for two. Let's say this. X, Y is in R. X has relation with Y, or X, R, Y. Those three notations are the same. So no matter which one they gave to you, I hope you understand what they mean, okay? They are the same thing. It's just different notation. Anyway, let's go back to this. This will give us A plus 2D equal to C plus 2B. Now you want to consider C plus 2B. Well, this equals to A plus 2D from here, okay? So this implies that CD has relation with AB. Number 3, transitive. Suppose AB has relation with CD, CD has relation with EF. You want to show AB has relation with EF. Based on this, you know A plus 2D equals to C plus 2B. C plus 2F equals to E plus 2D. And you want to show that A plus 2F equals to E plus 2B. Okay? So that's what you can do since you see A, 2F, B, where's E, 2B. Let's just add them together. You'll get A plus 2D plus C plus 2F equal to C plus 2B plus E plus 2D. And you can cancel out C, cancel out 2D, which will give you exactly what you want. A plus 2F equals to E plus 2B. And this implies that AB has a relation with EF. So it is transitive. Therefore, the relation is equivalence relation. Equivalence. Okay, I think that's it. I left a lot of questions for you. You don't have to do all of them, just pick the ones you think you don't know how to do. I mean, all the questions are quite similar. I don't think you have enough time to do all the questions. And there are a lot of questions on your textbook as well. Just try to do as many problems as you can. And that's the end of my video.